Assalamualaikum and good day to all. Our group will be presenting and elaborating on the two sample independent t-tests where the members consist of NUR KAMILIA ARISYA BINTI NIZAM. Number matrix is 227723. NUR RAIHANA BINTI MUHAMAD FIKRY 227710. MUHAMAD Syahmi bin BORHAN 227554. And lastly, ARDINA RAUQAH BINTI NASRUN 229014. An example of a situation that can be integrated in this clause would be a situation where imagine you are a commercial farmer preparing for the next growing season. You have two fertilizers options on the market. For example, fertilizer A and fertilizer B, where both of them claim to be effective, but they come at a different cost. Choosing the wrong one could mean either wasting your money, reducing your crop yield, or even damaging your soil. You need solid evidence-based data to make the right decision and not just through the marketing claims. And that is precisely where statistics becomes the key in unlocking this question. The table attached is the data on the effect of the fertilizer type on plant height, where sample size is 20. This brings us directly to our third research problem. We have two independent groups of plants. One group is treated with fertilizer A and another group treated with fertilizer B. Both groups were grown under the same environmental conditions where they were given the same soil, same amount of water, and the same amount of intensity of sunlight, so that the only difference between them is the type of fertilizer used. After a set growth of period, the height of each plant was measured in centimeters, where we are now left with the crucial question of, is the average height of plants treated with fertilizer A different from the average height of plants treated with fertilizer B? Now, our statistical analysis proceeds according to 5 sequential objectives. First, we determine whether a statistically significant difference exists in mean plant height between the two fertilizer groups. Secondly, we select the appropriate test, which is the two-sample independent t-test based on our study design. Third, we verify that our data satisfy the assumption of normality and homogeneity of variance required for valid inference. Fourth, we compute and correctly interpret the test statistic, p-value, and accompanying confidence interval. Finally, we translate our findings into a clear evidence-based recommendation that distinguishes between statistical significance from practical and economic relevance. The reasoning as to why t-test was chosen as the most suitable statistical method was because this situation features two independent groups, a continuous outcome variable, and a mean comparison objective. It is the most optimal parametric procedure for this design, offering greater statistical power than non-parametric alternatives when assumptions are met. The t-test directly quantifies whether the observed mean difference exceeds what would be expected by random chance, making it the most appropriate and interpretable tool for our fertilizer comparison. The t-test is an inferential tool that evaluates whether an observed mean difference between two groups reflects a genuine effect or merely sampling variability. Its validity, however, rests on 4 key assumptions. The outcome variable must be measured on a continuous or ordinal scale, or the sample must be drawn randomly from the broader population of interest. The data within each group should follow an approximately normal distribution, characterized by a symmetric bell-shaped curve. Finally, the variances across groups should be roughly equivalent, a condition known as homozygosity. These prerequisites must be checked before proceeding with the test to ensure the integrity of our conclusion. Computing a t-test requires 3 essential inputs from our sample data. First, we need the mean difference, the absolute or sign differences between the group averages. Second, we require the standard deviation for each group, which quantifies within group variability. Third, we must know the sample size, which is the number of observations in each group. These 3 values, means, standard deviations, and sample sizes, are the sole inputs needed to calculate a test statistic and determine whether the observed difference is statistically significant. The null hypothesis is the cornerstone of everything we're doing here, so it's worth understanding exactly why we need it. Our null hypothesis states that there is no difference in mean plant height between the two groups mathematically, so meaning that the min A equals to min B. We don't start by trying to prove the fertilizers are different. Instead, we assume they're the same and then ask, given that the assumption, how likely is it that we'd observe a difference as large as the one we actually see in our data? That probability is the p-value. If the p-value falls below our threshold, which is 0.05, the data will tell us that null hypothesis is impossible and we reject it. Now, to correctly compute that p-value, we need to account for one more important concept, which is variance. Variance tells us how spread out the height measurements are within each group. High variance means plants in the same group grew to a very different heights, which make it harder to say confidently that a difference between groups is real and not just random fluctuation. In the pooled t-test, we combine the variances from both groups into a single weighted estimate called the pooled variance. This pooled variance feeds directly into the standard error, the denominator of our t-statistics. If one group's variance is drastically larger than the others, that pooled estimate becomes unreliable. That's precisely why, before running the test, we must verify that the two groups have roughly equal variance, an assumption we test formally with the Levin's test.
Before we perform any statistical test, we need to understand something called assumptions in statistics. In statistics, assumptions are basic conditions or requirements that must be satisfied before we can trust the results of a test. If these assumptions are not met, the result of the test, such as the p-value, may not be reliable or accurate. So in simple terms, assumptions are like the rules of the game, and the independent t-test only works properly if these rules are followed. These assumptions are important because they ensure that conclusions we make from the test are valid. If the assumptions are violated, we may end up with misleading conclusions such as thinking there is a difference when actually there is none. Now, for the independent t-test, there are three main assumptions we need to consider. The first assumption is independence. This means that each observation in the dataset must be independent from one another. In our study, each plant grows separately, and each plant is only assigned to one fertilizer group, either fertilizer A or fertilizer B. So there is no relationship between individual plants, which satisfies the independence assumptions. The second assumption is normality. This means that the data in each group should be approximately normally distributed. A normal distribution is the classic bell-shaped curve, where most values are concentrated around the mean, and fewer values appear at the extremes. This assumption is important because the t-test is based on the idea of normal distribution, especially when sample sizes are small. In practice, we can check this using a histogram or a QQ plot, or normality tests such as Shapiro-Wilk test, Lilliefors corrected chaos test, and Kolmogorov-Smirnov test. To the to do the histogram. So first we have our set of data from fertilizer A, fertilizer B, which n equals to 20. So then we manually input our bin range and calculate the frequency for both fertilizer A and fertilizer B. Now to get our histogram, basically we just need to select our data, go to insert, recommended charts, choose this one and OK. And voila, we got it. Then we can do some alteration and improvement of the chart. Then we can get something like this. So this is the histogram of plant height treated with fertilizer A, showing a bell-shaped graph. And this one is for B. We use the same method, and we get also
a bell-shaped curve.
The third assumption is homogeneity of variance. This means that both groups should have similar variability or spread in their data. In simple terms, the heights of plants in fertilizer A should not be extremely spread out compared to fertilizer B. If one group has very consistent values while the other varies widely, the assumption is violated. We usually check this using box plots or statistical tests like Levin test or F-test. Now, above me are the box plots that we made.
Now I will show you how to do box plot using Excel. So we use this to compare the homogeneity of variances. So we just choose our data, go to insert, go to charts, and choose box and whisker. And that's it.
In our fertilizer experiment, we can evaluate these assumptions. First, independence is satisfied because each plant is independent and randomly assigned. Second, normality is approximately satisfied because plant height data follows a bell-shaped distribution in the histograms. Third, homogeneity of variance is also reasonable because both groups show similar spread in plant height value. The box plot shows similar variability between the two fertilizer groups. The interquartile range and whisker lengths are comparable, indicating that the homogeneity of variance assumption is reasonably satisfied. Therefore, we can proceed with the independence test confidently.
Here is my overview in what I will be covering in my demonstration part. First, I will show you the raw data for both fertilizer, and second, I will run the Excel for the t-test and show you what's the result. And the final step is show the chart to visually compare both of the group. So let's begin with step 1. Now let's look at our raw data. There have 20 plants in each fertilizer. So our sample size total is 40 plants. So we are trying to answer the research question, which is, does fertilizer A produce a different mean plant height than fertilizer B? As I shown in the slide presentation, there have two different data, which is fertilizer A data and fertilizer B data. And before we run the test, we are using the state hypothesis, which is the first is null hypothesis that state that there is no difference in mean plant height between fertilizer A and fertilizer B, while the alternative hypothesis shows that there is a difference in mean plant height between fertilizer A and fertilizer B. And we will be using a significance level of 0.05 for our test. Now let's move to step 2, where I run the t-test using the Excel formula. First, I use the average function to get the mean for each fertilizer. For fertilizer A, the mean is 20.9 cm and fertilizer B is 25.10 cm, and the mean difference is 4.15 cm. Next, I use the var_s function to get the variance for each fertilizer, where the variance for fertilizer A is 4.936 and fertilizer B is 6.20. And next, I will use count to confirm that we have 20 groups for each observation. Then I calculate the pool variance, and it's giving 5.56 and the standard error is 0.755. Next, I calculate the t-statistic by subtracting the mean and dividing the standard error, which giving negative 5.50. And the degree of freedom is 38. Next, I use the this 2t function to get the p-value, which is 0.0000184, which shows that it is less than the significance level of 0.05. This shows that there is a significance difference between both fertilizer, and it giving that fertilizer B is much taller than fertilizer A. Let's look at step 3, which is I have attached a chart to show that the mean plant height for each fertilizer type. So now let's take a look at the visualization. For the chart, there have two boxes, which is the boxes for fertilizer B is sitting much higher than box for fertilizer A. Also, they give a minimal overlapping, which suggests a clear difference between these two groups. And this shows that the visual chart is actually confirm the t-test what it already shows us. And the t-test and this visual chart jump to the same conclusion, which is plant B have a higher mean plant height compared to plant A fertilizer.
Good day everyone. Today and right now, I will present to you the interpretation of our two sample independent t-tests. Based on our demo, the t-test produced a t-statistic of -5.628 with 38 degrees of freedom. The corresponding p-value was 0.0000184, which is much smaller than our significant level of 0.05. The t-statistic itself measures how different the two group means are relative to the variation within the groups. Since the absolute value of our t-statistic, which is 5.628, is greater than the critical value of 2.024, the differences between the two fertilizer is statistically significant. On to the next is the p-value, which tells us the probability of obtaining this result if there were actually no difference between the fertilizer. Because the p-value is far below 0.05, we will reject the null hypothesis. This means there is sufficient statistical evidence to conclude that a significant difference exists between fertilizer A and fertilizer B in terms of plant height. Now, the mean difference between the two groups was 4.15 centimeters, with plants treated using fertilizer B, which growing much more taller on average than those treated with fertilizer A. From a practical perspective, an increase of 4.15 centimeters suggests better plant growth performance. Therefore, based on both statistical and practical consideration, fertilizer B is recommended as the more effective fertilizer for promoting plant height. That's all from me. Thank you.